G'day! Today we're going to extend our discussion of the unit circle and trigonometry to the idea of right triangles. We have a unit circle, then the radius is always 1. We defined sine and cosine based on the x and y coordinates of a triangle inside the unit circle. And so if that circle has an angle theta in standard position, then we call cosine the length of the x part of that triangle, and the sine of theta is the length of the y leg of that triangle. We're going to extend that today to triangles which are similar to the one you can see on the screen. So you can see this green triangle is similar to the yellow triangle, which means that it contains the same angle at the origin here. This same angle is theta, but it's longer in every dimension. And so the similarity tells us we can compare those lengths. So let's give names to the lengths. Compared to that angle theta, I can think of this side over here, essentially the y value along this triangle, as the opposite side. And we can think of this as the adjacent side. It's adjacent to the angle. This is the length that's adjacent to the angle. This is the length which is opposite the angle. And then the length up here, the hypotenuse, well, let's just call it the hypotenuse. And given those three things and the fact that these two triangles are similar, we can write down some relationships. So using those properties of similar triangles, we know that similar ratios must be the same. So the ratio of this length, sine, to the ratio of the hypotenuse of the small triangle must be the same as the ratio of the length of the big triangle to the hypotenuse of the big triangle. So sine over 1 must equal the opposite over the hypotenuse for the big triangle. Similarly, cosine, the ratio of cosine, the x length here, to the length 1 must be the same as the ratio of the adjacent length to the hypotenuse. And we can build a similar thing for tan. The ratio of the sine divided by the cosine, the ratio of these two angles in the triangle, must be the same as the ratio of these two angles in the triangle. So tan over 1 must be opposite over adjacent. So we can put all of this together, and just dropping the ones, we get a simple relationship between the sines and cosines of the angle theta in this unit triangle here, or in this little triangle, with the opposite adjacent and hypotenuse lengths of this bigger triangle. We can of course remember this using SOHCAHTOA, and it's just giving us the abbreviations of the first letters here. So the sine is opposite over hypotenuse, and so that's the sine is opposite over hypotenuse. The cosine is adjacent over hypotenuse, cosine is adjacent over hypotenuse, tan is opposite over adjacent. Here we go. And so this helps us remember that these two ideas are completely interchangeable. So let's use this idea to calculate some trig functions. Given the cosine of an angle, this is similar to what we've done before. We want to find the sine and the theta of that same angle, sine and tan of that same angle theta. So we can think about this by actually building a triangle. And we're going to build a triangle, and we're going to recognize the identity we have. The cosine of the angle theta is going to be, well, SOHCAHTOA is the adjacent over the hypotenuse. And so I'm going to treat this by building a triangle that has an adjacent of 3 and a hypotenuse of 7. So I'm going to think about building this angle theta inside this right triangle where the adjacent length is 3, and here's the adjacent length because this is the opposite length, and the hypotenuse is the square root of 7. Now from our trig identities, we know cosine squared plus sine squared is equal to 1. We could find sine that way, or we could use the triangle and say that, well, we know that the sine of theta is then the opposite over the hypotenuse, but we don't actually know the opposite, but we do have a triangle. And we know that on a triangle, that 3 squared plus that opposite length squared must equal 7 squared. And so we find the opposite sign just using the Pythagorean theorem. This is 2 times the square root of 10. And so there's the opposite side, and that means we can write down what sine is. It's 2 square root of 10, square root of 40, divided by the hypotenuse, which was 7. And using a similar calculation, we can calculate that tan, which is opposite over adjacent, well, the opposite again was 2 root 10, and the adjacent this time was 3. So we built a triangle which embodied this relationship we were given about the cosine of theta, and that allowed us to find sine and tan. Now, we used the fact that theta is acute because we're in the first quadrant. And if we're in the first quadrant, we know that sine and tan and cosine, well, they're all positive. And so taking this square root was no issue. We're literally talking about a triangle, and these numbers we're dealing with in this interpretation are lengths. This opposite we're building is the length of the side over here, and it is definitely a positive number. It's 2 times the square root of 10. We can always use this right triangle idea to redo some of the kinds of problems we were doing in the previous section. The only issue here, though, is we've got to worry about quadrants, and when we're dealing with right triangles, we're really talking about acute angles. So we're going to use reference angles here to address the problem where the tan of t is minus 2, so t is not an acute angle, because in the first quadrant, where t would be acute, tan has to be positive. So we're going to introduce the idea of the reference angle. We're going to call it theta here, and this is the angle we know. So we're going to say that we know that's acute. So we're going to say that tan of theta, is 2. And now we can build a triangle for that statement. So using this idea of SOHCAHTOA, we know that tan is the opposite over adjacent, and tan, in this case, tan of theta is 2. So I'm going to write that as 2 over 1, and then I'm going to represent this angle theta in the triangle with this idea. If this is the angle theta, then the opposite is here. I'm going to call it 2. The adjacent is here. It's going to be 1. By Pythagoras, this must be 2 squared plus 1 squared, which is the square root of 5. So we've got all three angles, and that immediately tells us, for example, that the sine of theta, again looking at SOHCAHTOA, that's the opposite over adjacent, the opposite over the hypotenuse, and plugging those things in for our angle here, the opposite is 2, the hypotenuse is the square root of 5. Similarly for cosine, we get the adjacent over the hypotenuse, and the adjacent is 1, and the hypotenuse is still the square root of 5. Well, that's all very nice, but that's not what we were asked for. We were asked for the tan of t. And so what we're looking at here is, again, the unit circle. And I've placed our yellow triangle in the unit circle. You know, that's length 1, so that must actually be the x value there in the unit circle. That's 1. There's our theta. We've got a length of the square root of 5 coming up here. So what we're actually interested in is this smaller triangle inside the unit circle here. But we're looking at tan is negative, so the corresponding where tan is going to be negative 2, tan of t is negative 2, we must be looking at a line that's over here in the second quadrant. So t is going to be like this. But we could use our reference angle theta, because theta is a reference angle, theta is the angle that's in here. We can then say, well, that tan of t, we know that's negative 2. That was easy. We know the sine of t must be, well, it's either positive or negative, the sine of theta. And we're in the second quadrant, so sine is positive. And the cosine of t must be positive or negative, the cosine of the reference angle, which was theta. We're in the second quadrant, so cosine is negative. So we can just write down the results for this based on our knowledge of where t is. But we used the reference angle theta. But the whole time t itself was in the second quadrant. So we're able to find here the sine and the cosine and the tan, and we could continue then to find all of the other trig functions. For example, the cotangent of t would be 1 over tan, so that would be minus 1/2. The secant of t would be 1 over cosine of t, which would be minus the square root of 5. The cosecant of t is 1 over sine of t, which is the square root of 5 over 2. So using this idea, we can again find all of those trig functions. We can also use this idea to look at a triangle and find all of the information inside a triangle. It's called solving a triangle. So let's solve this triangle that's shown. We're given one angle in the triangle, and we're given one of the lengths. Well, actually, we're given two angles, because we know that this is a right triangle, and so this is a 90-degree angle. And so we have a property that tells us the third angle immediately, because the sum of all the interior angles of any triangle is pi radians, or 180 degrees. And I've given you a 58 degree in here, so let's use degrees. That tells us that when we take the sum of the interior angles for this particular triangle, we're going to get 58 plus 90, there's the right angle here, and plus the remaining angle, let's call it theta. And that angle has to give us something that sums to 180 degrees. And so when we do that, we get that theta is 32 degrees. So our next job is to find all of the lengths. And if we can find all of the lengths and all of the angle, then we've solved the triangle. So let's give them names. Let's call this, well, this is the hypotenuse. Let's call this one C, and maybe this A. And we know several things. We know that A squared plus 4 squared is equal to C squared. We've always got the Pythagorean identity. And we have some trig identities. Now, we don't know either A or C, so the Pythagorean identity isn't enough right now. But we can use the trig identities. I know angle is 58 degrees and this angle is adjacent to it. We also know that the remaining angle in the triangle must be 32 degrees. So let's use the 58. If we know the adjacent angle, then we can use SOHCAHTOA with some length that involves adjacents. So the cosine and the tangent both involve adjacents. So let's start with the cosine. We know the cosine of that angle 58 degrees has to be adjacent over hypotenuse. Well, the adjacent is 4 and the hypotenuse is c. So rearranging that, we know that c is, putting the c over here, is 4 divided by the cosine of 58 degrees. Another way of writing that would be it's 4 times the secant of 58 degrees. Now we could work that out, but this is an exact value, so we can just leave it that way and then find a using that information. Again, we could go back to the Pythagorean theorem and plug in what c is, or we could just use the fact that we know, let's say 58 degrees, and we know the adjacent length, and we want to know the opposite length, so something that links those two is tan, because we know that tan of 58 degrees is equal to, well, the tan is opposite over adjacent, the opposite is a, the adjacent is 4, and so just solving for a, we can write a is 4 times the tan of 58 degrees. And those two things together tell us everything about the triangle. We know 58 degrees and the corresponding length is a, which is 4 times tan of 58 degrees. We know we've got an angle of 32 degrees and the corresponding length is just 4. And finally, the right angle of 90 degrees, the corresponding length opposite is the hypotenuse, and it was 4 secant of 58 degrees. And we could approximate those, and that would give us about 6.4, 4, and about 7.54. So just plugging those into a calculator. But these exact values are fine. These exact values and corresponding angles solve the triangle. They give us all lengths and all angles. So finally, let's look at an application. Suppose you're a surveyor and you want to find the height of a mountain. And we can go down on the ground here and we can actually take a few measurements. So suppose we actually look up at the mountain and we measure that the angle of that peak of the mountain compared to the horizontal ground is about 28 degrees. So we take one measurement, we find the height of the mountain looks to be 28 degrees above the vertical. We can do this with some surveyor's equipment. And then we walk towards the mountain. Imagine we walk 1 mile towards the mountain and we take a new reading here. In other words, we've walked 1 mile closer to the mountain. I don't actually know how far away I am from the mountain, but we walk 1 mile closer to it and then we take another reading. And when we take that second reading, we find the angle is 45 degrees. Well, what we end up with is a pair of triangles. We still don't know how far we are from the mountain, but that's not actually important because we can use trigonometry to find the height. Using the information we do know, I can resketch the picture over here. We want to know the height h. I'm going to add one more variable in. I'm going to call this length along here, let's say x, and then we can write down some trigonometric combinations of these different ideas. Because you'll notice, for example, that tan of 45 degrees is, well, using SOHCAHTOA, we know tan is opposite over adjacent, so looking at the angle 45 degrees, opposite is h, and adjacent is x. Similarly, in the bigger triangle, that was inside the purple triangle, but inside the bigger yellow triangle, we also know that tan of 28 degrees is, well, opposite, again, is h, and the adjacent is this total length, which is x plus 1. So our job here is to solve for h, because we have everything we need. We have two equations here that involve two unknowns, but we know tan 45, we know tan 28, and so we can solve for h here. So that's your homework. Find h as a length. Find the height of this mountain. That's one of our homework problems for today. So thanks for tuning in.